In this paper, we provide an analytical characterization of the coverage region for a 2-user downlink communication system utilizing a simultaneously transmitting and reflecting reconfigurable intelligent surface, STAR-RIS. The system model includes a single antenna base station serving 2 single antenna mobile users, with the direct link between the base station and the reflecting user blocked due to obstacles. We consider both non-orthogonal multiple access, NOMA, and orthogonal multiple access, OMA, schemes, under the energy splitting, S, protocol. The signal to interference plus noise ratio, SINR, for the successive interference cancellation, SIC, process and the SINR at both reflecting and transmitting users are derived. Furthermore, we use a gamma approximation to derive equivalent channel distributions, which is reportedly more accurate than the central limit theorem, CLT, approximation. Our numerical results show that the proposed analytical expressions are rather accurate and confirm that STAR-RIS can significantly enhance the system performance in terms of the coverage region for the NOMA scenario compared with the OMA scheme. The authors analyze a downlink STAR-RIS-aided NOMA, OMA communication system, deriving analytical expressions for the coverage regions of users in the transmission and reflection planes of the STAR-RIS under the energy splitting protocol. The coverage region is defined as the geographic area where reliable communication is guaranteed, ensuring rates RR greater than 0 and RT greater than 0. The authors exploit the concept of coverage region provided in 11 Def. 2, and assume the base station, BS, is located at the origin of the two-dimensional coordinate, with the STAR-RIS placed at a fixed distance d from the BS. Theorem 1 provides the coverage region for users and OOD in a STAR-RIS-aided NOMA communication system, given by equations 10 and 11, respectively. These expressions are derived using Maher's G function and involve expectations over the random equivalent channel weak. Theorem 2 provides the coverage region for user UK in a STAR-RIS-aided OMA communication system, given by equation 21. The proof follows similar steps to Theorem 1. Numerical results are presented to evaluate the analytical expressions, assuming a STAR-RIS with n elements placed 10 meters away from the BS. The results show that as n increases, the STAR-RIS covers a larger area for users and OOD. The authors also observe that user OOD can be located in a region further away from the STAR-RIS compared with user and that the STAR-RIS under NOMA scenario provides better performance than the OMA case. The behavior of the coverage region is presented in terms of the transmit SNR rho and the square of the transmission, reflection coefficients beta 2k. The results indicate that applying the STAR-RIS into NOMA networks improves the system performance in terms of the coverage region. In conclusion, the authors provide a comprehensive analysis of the coverage region in STAR-RIS-aided NOMA, OMA communication systems, highlighting the benefits of using STAR-RIS in terms of coverage area and system performance.